Welcome to the fourth video of today's lecture. In this video, we are going to talk about system-level network simulation. And this is necessary because complex systems are often way too complicated to be simulated using CFD methods. You can see this on the right-hand side. This is an example of a centrifugal-driven microfluidic chip. So you have the center of rotation here, and what is illustrated here is a network of microfluidic chambers and channels. And you can see that the system is partly filled with a liquid indicated in this bluish greenish color, and that you have air in the rest of the chambers. Here, for example, you have compressed air, and you can immediately see that this is a highly complex system. So if you would like to model this with CFD, you would have to construct a very complicated mesh. You have areas where you have quite large volumes, then you have very narrow channels. This means it's a lot of computational effort. Then you have free surfaces, meaning that you have gas and water, and you would need to model this as well. So this is highly complex. And the complexity can be reduced if you refer to system-level network simulations. And the idea here is that you use network models for thermal or hydraulic problems that are analogous to electric circuit network models. And this is illustrated on the right-hand side. Here you can see how the equivalent network model for this complex chip would look like. You can see the corresponding chambers, which you also saw on the left-hand side, and you can see that the channels are represented by this type of resistors. And this example illustrates quite nicely the basic idea of this whole approach, which makes it able to simulate even complex system and study their dynamics. And to construct these networks, we can use the electric thermal or the electric hydrodynamic analogy. And this is based on the concept that fluid mechanics, as well as thermal transfers, deal with transport phenomena that are very similar to electrodynamics. And this means that the precise solution of the governing equations is highly challenging. So for fluidics, that would be the Navier-Stokes equation. For thermal effects, that would be the energy conservation, for example. And in electrodynamic systems, that would be the Maxwell equations. And all those problems have in common that sometimes the information on global values, for example, the total volume flow, is often sufficient, and the actual distribution of the local field variables is not necessary. So the basic idea is also illustrated on the right-hand side. Instead of looking at your channel, which is quite complicated and has, for example, this parabolic velocity flow profile, you are now not interested in all those details, but you're more interested in the flow rate through my channel and what is the pressure drop. And this leads us to the basic concept of the fluidic network approach. We go from the distributed variables to integral quantities at selected points. And there are two types of the variables we need to talk about at those discrete nodes. The first type is the across variable, which is voltage or pressure. And the second type of variable is the through variable, which would be the current, or in the hydrodynamic world, it would be the mass flow. And instead of solving the partial differential equation system, we now can solve the transfer function of the individual nodes or elements, which is way easier. And the transfer functions are usually represented by ordinary differential equations. And this principle can now be used to actually set up a network simulation approach. And this is done by replacing the actual system with a discrete set of ideal elements. For example, you can replace elements which have a resistance type of behavior with a resistance, and so on. So you should know these elements: resistance, inductance, capacitance, and the diode already from electrodynamics. And what you now do is you look at your system and you think of how the individual components behave, and then you set up such an equivalent electric network, and those can be simulated or calculated quite easy. And the connection between all those elements here is done by applying conservation laws, the so-called Kirchhoff laws. And you should know these already. The first one is that the sum of the currents at a node, for example, at this node, must be zero. So the sum of this current, and this current should be zero at this point. This is something like the mass conservation. And then that you have the sum of all voltages in a closed loop must be zero. So for example, the voltage in this loop must be zero. And now you need the transfer functions. And the transfer functions are the functions that connect the across and the through variable for each element type. So the transfer function of this resistor, for example, would be the function that connects the current through this resistor with the pressure drop over this resistor. The basics of this approach are summarized in this slide. Here you can see the governing equations for the electrical world, which would be the Maxwell equations. For the fluidic problems, it would be the Navier-Stokes equations. And for thermal problems, you usually have the energy equation. And the cross variable in the electrical network approach is the voltage, which is defined like this, the difference in the potential. And it's quite similar in the fluidic world. Here you have the hydrodynamic potential, which is the cross variable. And the hydrodynamic potential in the fluidic network theory is defined like this. It's basically just the total pressure, which consists of the static pressure, the dynamic pressure, and then a pressure which is induced by height change. And in thermal problems, the cross variable would be the temperature. And analogous to the cross variable, you have a through variable. And in electrical systems, this is the current, which is just defined like this. This is the current density multiplied by the cross section. And in the fluidic world, this would be the volume flow. And analogous to that, we have the heat flow in thermal systems. We will now discuss the individual fluidic elements, and we start with the fluidic resistance. The electric hydrodynamic analogy for resistance is quite simple. In the electric world, we have the loss of voltage along a conductor, and in the hydrodynamic world, we have the loss of hydrodynamic potential along the channel. And this is illustrated here. This is just the definition of the hydrodynamic potential. And if you want to model this, you first have to look at a channel like this. So how do we get from a channel like this to a representation in the network model? And this is also quite straightforward. So if you want to model dissipative loss, we first have to apply some simplifications. The first simplification is that our velocity profile is constant. And that means that this is fully developed, so it does not change. And the second simplification is that we only use flat geometries, meaning that the channel does not go up, so H1 and H2 are constant. Using those simplifications, we can state that the hydrodynamic potential equals the static pressure. And if we apply this, we can calculate the ideal resistance, because the ideal resistance is always given by the ratio of the across variable to the through variable. So the ideal resistance in the hydrodynamic case would be the hydrodynamic potential divided by the volume flow, which is then nothing else but the static pressure divided by the volume flow. And you can instantly see that this is similar to the electrical network models, where we have the electrical resistance, which is defined as the voltage drop by the current. Usually, you would like to relate the hydrodynamic resistance of your network element to the channel characteristics, such as the cross-section or the length. And for Poiseuille flow profile, that means you have laminar flow in a pressure-driven channel. This can be done using this formula. In general, you can say that the fluidic resistance scales like this, and it depends on the channel geometry. And the channel geometry is represented by this geometry factor right here. And to evaluate the value of this geometry factor, at least for circular channels, we can have a comparison between the analytical solution for pressure drop in pipes and the network simulation. And in the network simulation, the pressure drop inside a pipe would be this expression. And We know already the analytical solution from the previous lecture, and the analytical solution looks like this. So this is a pressure drop in a pipe when you calculate, when you solve the Navier-Stokes equation for laminar flow. And if you compare those two expressions, you can immediately see that the geometry factor for a circle is 8p. And of course, this changes if you have rectangular channels or other channels. Now that we have covered fluidic resistance, I would like to give you an idea about thermal resistance as well. And here it's quite similar. You have the electric thermal analogy for resistance. In the electric world, you have the loss of voltage along a conductor. In the thermal world, you have a loss of temperature along a conductor, and this is illustrated right here. And the modeling approach is also quite similar. You again take the ratio of the cross variable to the through variable. And if you do this, you can see quite easy that it comes to this expression. And the resistance of a planar wall can be expressed like this. You have the temperature difference divided by the heat flow. And if you do those calculations and look at this planar wall, you end up with this expression. We continue with the fluidic inductance. In the electric world, changes in the current in a conductor creates a voltage that is opposing that change. You have a quite similar effect in the hydrodynamic world. Here, the response of a fluid to external forces, which is mostly pressure, is not instantaneous because you have inertia. And we can model inductance by saying that hydrodynamic inductance relates pressure with mass flow. And to illustrate this, I have prepared a picture on the right-hand side. Here you can see a channel, and you start with fluid at rest. And now you push part of the fluid, a small element, with the force dF into the right direction. And then this creates mass flow inside this channel. And we can now analyze how the mass flow and this force relate. You can say that the volume, the change in volume flow, multiplied by the density divided by the cross-section multiplied by dx equals the inertial pressure. And this means that inductance of a channel or of any geometry determines how fast the mass flow can follow pressure changes. And you can model inductance in your network using this expression. And you can immediately see that for the inductance, we have a similarity between the electrical world and the hydrodynamic world. So in the electrical world, you have this voltage that counteracts your charge movement. And in the hydrodynamic world, you have this pressure which counteracts immediate movement due to inertial effects if you apply an external pressure source. So we can continue with the next element, which would be capacitance. And we start with fluidic capacitance. And here, just to remind you, in the electric world, capacitance is the storage of charge due to a voltage difference. And this would correspond in the hydrodynamic world to the storage of fluid volume due to pressure difference. And this is explained on the right-hand side. Imagine you have a channel, and in this channel you have a gas bubble. So this is the blue part is liquid, the white one is a gas bubble. And if you now increase the pressure, the bubble volume will decrease, and you will be able to store more liquid inside this channel. And there are different phenomena that lead to fluidic capacities in systems. The first one is, of course, the compressibility of media, as it was illustrated here. Here you have the compressibility of the gas bubble. And another source of capacitance inside a fluidic chip could be flexible walls or membranes. And you can model capacitance by this expression. There also exists thermal capacitance. And in the thermal world, capacitance means the storage of heat due to temperature difference. This is illustrated on the right-hand side. So you have a conductor, and now you store more heat in this conductor by heating it up. And you can model thermal capacitance for an ideal gas, for example, using this expression. Here you can account for the volume of your gas, the density of your gas, and the heat capacity of your gas. I would like to end this section with the fluidic diode, which would correspond to a valve. In the electrical world, you know that a diode conducts current only in one direction. So this is expressed, for example, here. This diode only allows current in this direction and not vice versa. And in the hydrodynamic world, you would call this a fluidic valve. And this is illustrated on the top. So here you see two images. It depicts the same valve. And on the left-hand side, the valve is in forward operation. That means that there is flow. And the valve itself consists of a membrane, which is here. And if the flow flows in this direction, it can displace the valve. And if you apply pressure in the opposite direction, the flow would push the membranes against this structure here. And as you can see now, the cross section is closed and there is no flow in the other direction. And the modeling approach is therefore quite easy. A valve always has flow resistance characteristics as well as capacitance characteristics and diode resistance characteristics. And this becomes clear. If you look again at this example, you can easily see that the fluid, even if it passes the valve, there will be some kind of pressure loss because it is an obstacle after all. Then you have, of course, a membrane, and the membrane always adds capacitance to your system. And then, of course, you have this forward operation and the backward operation. So you always have this diode characteristic. And this means you could model the valve, which we discussed here, using this electrical circuit equivalent model. And you can now say that the volume flow has this resistance characteristic, it has a capacitance characteristic, which can be expressed like this. And for the backward operation, you can just say that there is no flow rate. Using all those elements, you should be able to construct electrical circuit networks for hydrodynamic systems. And I would like to end this video with a short comparison between the CFD approach and the network approach. So we start with the CFD approach. Here we have a system of partial differential equations based on physical fields. This could be the Navier-Stokes equations, and those equations are solved numerically. And the result is continuous in space and time, but effort you have to put into your simulation corresponds to the mesh size, and it corresponds to the number of additional transport equations. And CFD is generally useful if you want to perform detailed studies of an individual component, or if you want to study distributed variables. For example, you want to know the pressure distribution within a component, or you want to know the temperature distribution inside the channel. On the other hand, there are the system-level network simulation approaches. And here we solve a system of ordinary differential equations, which are based on transfer function of the network elements. Those calculations or the results are discrete in space because we only solve our ordinary differential equations at the nodes, but the results are continuous in time. And this leads to the fact that those computations are quite fast, even for large systems. And those system-level network simulations are usually done if you want to study system dynamics, or if you want to study the interaction and coupling of components.